All right, let's get started. All right, so Happy New Year. And tonight I just picked some problems that are related to the topic equivalent expressions. So let's take a look at number one.
Okay. Um, all right. So there's a couple of ways to go about this one. This is a pretty hard problem, but the first thing is when they tell us that this is equivalent to something that looks like this, all that's telling us is that it actually factors because they're all whole number constants. So it means that it would actually factor. We would be able to break it up into its factors. So if we think about how we would go about factoring this first, we would do something called the AC method. So we would do 8 times 145. That ends up being 1160. And then to find K, we'd have to find two numbers that multiply to 1160 and then add up to K. So we just got to figure out, it says which could be K. There's not a single answer to K, there's a bunch of answers, and it wants to know which of these answers only one of them can work. So a natural place to start would be to just start multiplying numbers together to give us 1160, and one of them would be 1160 and 1, which would mean that if we added them together to get K, we would get 1161. So this 1160 is not possible. And then we go to 580 and 2. So I'm just trying to go in like an order here so we don't really miss any. And again, if I added these together, I would get 582 for K. So 580 doesn't make sense. And basically, we just kind of keep narrowing them down. I think if we do 1160 divided by 4, that doesn't work. 1160 divided by 5. Yeah. So another one that gets us close to one of these is 232 times 5. And again, if we subtracted these, we get 227, but we're not. We're adding them to get K. So that doesn't work. So kind of we're left with this. Or in the very beginning, if you just think of the fact that a way to get 1160 is 116 times 10, those added together give you 126. But it's, I don't know, what you either kind of like come up with that or you don't. So I just wanted to go over how you could kind of go in an ordered way to eliminate answers as well. But the bottom line is you have to know that this just is telling us that this factors, and we got to kind of remember how to factor using this thing called the AC method.
All right, that makes sense.
Good. All right. Number two is another kind of hard one. All right. So this one is again a tough problem, but you gotta get started somehow. So if they're saying these are equivalent, then I'm just gonna set them equal to each other. So I'm gonna do, whoops, I'm gonna do a to the x, b to the y to the point 0.5 is equal to the fourth root of a to the y, b to the x. And then clearly we're going to have to do some rearranging. It says which of the following is equivalent to this. So we're going to have to just do like a bunch of algebra to try to get this. And then eventually on the other side will be one of the answers. So the first kind of logical step would be just raising everything to the fourth power just to kind of get rid of this. So over here we get a to the x, b to the y. Well, zero point 0.5, when you raise a power to a power, you multiply. So zero point 0.5 times 4 is 2. And then the fourth power and the fourth root cancel. So you're just left with a to the y, b to the x. Then when you raise both of these to the second power, you get a to the 2x, b to the 2y, because again, you're multiplying. Okay. So now the idea is if I want an expression with just a in it, I want to get the a's on one side, and I want the answer to have b's in it, so I'm going to get b's on the other. So I'm going to divide each side by a to the y, and each side by b to the 2x. That's going to get divide this out and this. So now I have the a's on one side and the b's on the other. And then it's just about remembering exponent laws. Whenever you divide, you subtract your exponent. So another way to write this is a to the 2x minus y, which is where this comes from. And then on the other side, I get b to the x minus, this should be 2y. I did not write that very well. This was b to the 2y, so I should have been dividing each side by 2y. So this is x minus 2y. And then when we look, a to the 2x minus y is equivalent to b to the x minus 2y, which is a. All right, let's try this one. Okay, pretty hard one. Oh, no worries. We're only on problem 3. Okay, so for this one I'm going to go over something more like simple before we attack something like this. So I want us to take a look at maybe something like this. Imagine we had the absolute value of x minus 2, and we had to think about it as 2 different expressions, kind of like a piecewise function. So imagine we had a number, we knew our value of x was less than 2. So if it was a number less than 2, when we subtract 2 is going to be negative. And the absolute value of that is going to turn it into a positive, right? Absolute value is distance from 0, but what's actually happening is it's turning to a positive. Well, another way to turn something to a positive is to multiply it by -1. So if I were to do this, this would do the same job as the absolute value. So if you think about a number like 1, 1 minus 2 is -1. The absolute value of -1 is +1. If I plug in 1 minus 2 here, I get -1. -1 times the negative turns it to a positive. So it essentially does the same thing. Now imagine I take a number that's bigger than 2. That means that, like say 3, well, that number's already positive. So if it's already positive, the absolute value is unnecessary. So we could just leave it the same. So when they want you to write an absolute value expression as an equivalent expression for some inequality, basically they're having you do that. Notice none of the answers have absolute values in them. So we're in one of these scenarios where we're either replacing the absolute value with the negative of what it is, or we're leaving it the same. And then what's special about this h over a, or actually, let me go back to this. What's special about 2 is it's the value that makes it 0. That's kind of like the cutoff, where numbers less than it or greater than it are either going to make it positive or negative. So what's special about h over a is if we were to take ax minus h and set it equal to 0, we would get h over a, okay? And numbers less than this are going to make this negative, and numbers greater than this are going to make this positive. So we're really just focused on the fact that, so we have our -10. Then we're going to take the negative of this. So I'm going to kind of do that. I shouldn't use, that might get confusing. I'm going to use like a double parentheses. Then we're going to take the negative of ax minus h, then plus 12. Okay, so let me just reiterate all of this. The fact that x is less than h over a means that the inside of this absolute value is going to be negative. I need to flip it to a positive. I'm going to do that by multiplying by this negative. That allows me to get rid of the absolute value. And then when I look at my answers, well, if I distribute the negative here before I look at the answers, this makes this negative ax plus h. And then if I just rewrite this, negative ax plus h is the same as h minus ax. So the answer ends up being B.
All right, got it. That makes sense.
That made sense. Thank you.
Okay, good. So that's a pretty tricky one. Again, all the explanation, we didn't need all this at the top to actually do the problem. When you see a problem, like this is a pretty specific problem, but basically you're looking at it and saying, okay, am I keeping this ax minus h the same, or am I making it negative? And that's really the only thing we have to worry about.
All right, got it.
Okay, number 4. So try this one. Okay, so for this one, I'm just going to write it like this. So if it simplifies to it, that means it's equivalent to it. So this is another one of our equivalent expression problems. And what I'm going to do is just multiply each side by 6x plus a. So like if I multiply this side by 6x plus a, it divides out here. And then I multiply this side by 6x, plus a. Okay. So now I'm going to focus on this side. I'm just going to do multiply it out, or do a little bit of FOIL. So 4x times 6x is 24x squared. 4x times a is 4ax. 6x times b is 6bx. And then b times a is ab. And then I just kind of match it up to the other side. So obviously the 24x squareds match up, but that doesn't really help me. And then I think about this. Well, if I were to combine these, I would really be doing 4a plus 6b. That would be the coefficient of x. That has to equal 126. And then I need the constant term to equal negative 735. So AB has to equal negative 735. So we get to that step, and what we have to realize is, I'm just writing this down because I'm about to use Desmos. What we have to realize is we don't want to have to solve a system like this by hand. It's more work than it's even worth, especially on the SAT. So what I have here is a system to help me find A and B, and then I'm going to add A and B together. So I'm going to jump over to Desmos. And another important thing in Desmos, this might be obvious, but it needs to be said. When we plug things into Desmos, we need to use X's and Y's. So even though the system had A's and B's, I'm just going to change them to X's and Y's. So I'm going to do 4x plus 6y equals 126. That's the 4a plus 6b. And then I'm going to do AB, so xy equals negative 735. Then I'm going to zoom out. And now it seems like I have a problem. I have 2 answers. I'm not going to go back to the problem, but the problem did say that A and B had to be integers. So whenever you have a system that you solve for a problem and there's multiple answers, just make sure you look at the requirements, I guess, of the problem. So since they need to be integers, I can get rid of this answer. So now I know A is negative 21 and B is 35. So I'm going to jump back to the actual problem. And since A is negative 21 and B is 35, when I add them together, I actually get 14 for the answer. So it's a combination of like an equivalent expressions, but then you get to a system that is better off to just use Desmos to solve it. All right, take a look at number 5. Move it up here a little bit. All right. Okay. This problem is pretty difficult. Also, I'm going to do this, I guess, just kind of by hand. And then I'm going to show you a cool way to use Desmos using this thing called regression. But before that, I want to go over the other way to do it. So at first glance, it seems like, well, all we have to do on this side is to get a common denominator. So even though this isn't completely correct yet, I want to go over that, which would mean I'd need to multiply this by x minus 2, top and bottom. And then I need to multiply this side by x squared plus 4. Whoops. So if this were a school problem, this is all we would do. You just get a common denominator. The denominators have nothing in common, so you just multiply each by the other denominator. This is what makes this category of problem on the SAT challenging, because all they're saying is that these are equivalent. They're not saying it's like the most simplified version, so they get away with doing things like this. Notice that if I were to do x squared plus 4 times x minus 2, it wouldn't give me the actual denominator I have over here. Hopefully, a couple of things that we know algebraically that we can do quickly in our head is that this is really equal to x squared minus 4 times x squared plus 4, because this is a difference of 2 squares. So I have the x squared plus 4 in each of these, but what I'm missing is an x squared minus 4. Well, x minus 2 is part of that, and the other part of that is x plus 2. So we're actually combining this by not actually getting a common denominator. We're getting a common denominator, but we're not getting the least common denominator. So I need to multiply this also by x plus 2. So let me just recap that. So since our denominator over here is x squared minus 4 times x squared plus 4, I need to make sure that I have the same denominator over here. So this one has an x squared plus 4, so it really needs to be multiplied by both of these, which together create this. And then this one has an x minus 2, so it needs an x squared plus 4, and then also an x plus 2. And then they're going to have the same denominator. So for the rest of the problem, I'm going to ignore the denominator, and I'm just going to focus on the numerator, and that's going to help me get A, B, C, and D. So what this really is x squared minus 4. And if I multiply that by 2, that gives me 2x squared minus 8. Now over here, I'm going to have to, I can do it a couple ways. I can FOIL this and then multiply by 5, or I'm going to do it like this. I'm going to write it as, I'm going to distribute the 5 to this one, and then FOIL it with the x plus 2. So I get 2x squared minus 8. Then I have 5x cubed plus 10x squared plus 20x plus 40. And then combine like terms. 12x squared. I have just a 20x by itself. And then I finally have a plus 32. So now when I match this up to, again, there is a denominator in both of these, but I just ignored it. So this numerator has to equal this numerator. So therefore, that tells me that A is 5, B is 12, C is 20, and D is 32. And finally, they wanted me to do A plus B plus C plus D. So you just add them together. So 52, 64, 69. Yeah.
All right, that makes sense. Thank you.
Yeah, I understand too. Thank you.
Okay. Now, that is a ton of work. And I would not want to have to do that much work on an SAT problem. So I'm going to show you a different way. I just want to make sure I have it real quick. Okay. So let's jump over to Desmos. Remember our answers, 5, 12, 20, 32. And we're going to see how Desmos can kind of give this to us just almost directly. And this works with a lot of different types of these equivalent expression problems. that have these constants in them. The problem is, to do it correctly in Desmos, you have to use like the correct like syntax. So the first way to do regression is when we put everything in, instead of x, we're going to be using this like x sub 1, this like subscript. So the way you're going to do that is you 2 over, now instead of x squared, just write x1 squared. You don't have to do the subscript. If you just type x then 1, it'll automatically make it a subscript.
All right.
Okay. So I basically took the problem, the left side of it, and I rewrote it. And the only thing I changed was instead of x, I used x sub 1. So that's the first thing. Now, this is the next super, super important thing, or this won't work at all. So there's really like 3 things that are really, really important. First is that you make them x1s. Next is that you use this thing called a tilde or a little squiggly. That you use that instead of equals. Okay, this again just has to do with Desmos like syntax for doing this thing called regression. Now on the other side, I'm going to put the exact thing. So I have ax1 cubed plus bx1 squared. And again, I'm still using x1s for everything. Plus cx1, whoops, plus d. I put that in parentheses so that when I divided, it gave me the fraction. There's other ways to do it, but that's just how I do it. And then I have x1 to the 4th minus 16. Okay. So it takes a while to explain it, but once you get used to it, think about all the work we did on that other problem. Right now, we just have the exact equation that they gave us with our constants in there. X is replaced with x1s and a little tilde instead of the equals. Now, clearly, these answers are wrong, okay? So then what you have to do is you have to hit x1 equals and do a little bracket. And you have to make x1 equal to a bunch of values. Now, the rule here is however many constants there are, that's how many values you use. You have to allow x to be equal to. It has to do with like Desmos is behind the scenes, like solving a system. So if we have 4 unknowns, like A, B, C, and D, we're going to need 4 values. Another important thing is you never want to choose values that would make the denominator 0. So I can't use 2. And the problem actually said x is greater than 2, so I'm just going to choose values bigger than 2. So I'm just going to go 3, 4, 5, 6. And notice, when I'm not at 6, when I only put 3 values, I've got random answers. But as soon as I put the 4th value, I have the answers there that we found the other way. And then that's it. And if I change these to like, I don't know, like 6, 8, 10, 12, right? As long as I put 4 values that are not 2, because 2 would mess it up by dividing by 0, I will get the 4 answers that we got the other way. So it's this thing called regression that sometimes is a shortcut to doing those full like equivalent expression problems.
That makes sense. But I have one question. After the squiggly, I think it's called tilde. After that, if you put like any like equation with like variables, it would take it for any of them. It would give you possible values, or is it like specifically this one?
It has to be. It would be like X values, I guess, and then it can have these other letters as constants. It'll find all the constants given
Okay.
whatever values you plug in for the variable, which in this case is x1.
Okay, thank you.
All right, got it. Yeah, you're right. This way's a lot faster.
Yeah. You have to be really careful though, because unfortunately it doesn't always work. So, and the tough part of this is that sometimes you don't know it doesn't work until like you try it. So if we look back, and then we'll do it again on the next problem because it does work. But if we look back real quick to this one, if we remember when we did it in Desmos, like using the graphing way, and we actually did this algebra, there were two answers. And one of the answers didn't make sense because it was a decimal and it wasn't an integer. I did this problem earlier using this regression, and it didn't work because it would only gave me that answer. It only gave me the answer with the decimal. So for some of these, when there's more than one answer, the regression only gives you one answer, and that answer might not fit like the requirements of the problem. So it can be a little bit risky, but it also can be like, it can save a significant amount of time. So the reality is you should just know how to do regression in the Desmos, but it's not always going to be applicable. So yeah, we're just going to do it on this one. So I'll give you a couple minutes if you want to try it on your own using Desmos, and then I'll just do it real quick and you can see. And the idea here is you have two constants, so you're only going to have to make x1 equal to two numbers, but they cannot be 1 and -2 because those values would mess the whole problem up. So see if you can figure that one out. Okay, so let's try to do this problem just in Desmos first. So we just kind of put it in as is, but we do x1. You also got to really like think about how good you are at like how quick you are at like typing these. Oh, whoops! See, I messed up. I didn't put I put the equals, so then I go back. It'll tell you like there's an error. Then you do that, and now all this shows up. And then again, we're going to let x1 equal some values, and Desmos is going to plug those values in and then solve the system for the missing a and b. So since there's two unknowns that Desmos is solving for, we're going to pick two values. We don't want them to be 1 or -2, so I'm just going to pick 2 and 3. And as soon as I do that, it snaps in to tell us that a is 7 and b is 5. And that's what we would have gotten doing it the other way. So first of all, any questions about that?
Nope, makes sense.
No, that made sense.
Okay. So we jump back. And then Desmos just told us that it was 7 and 5. So the answer to the question is a times b. So the actual answer is 35. So now, again, some of the younger kids are going to type a lot faster than me. And if you could do that super fast, then do it that way. But I personally would have done it the other way. So I just want to, again, the test is all about decision making. You don't want to always use regression because sometimes it might not work. And sometimes it might actually be faster. If you can get to the point where you realize here that the way you would combine these is by getting a common denominator. And the common denominator in this case would simply just be this. And you realize again that the denominators don't really matter because they end up all canceling out. You might just be able to jump right to this step where you get 4x plus 8 plus 3x minus 3, and you get 7x plus 5. So clearly A is 7 and B is 5. So it is also possible that in a problem like this, doing it this way might be faster. But certainly in this problem, if you understand regression in Desmos, that is significantly faster. So Desmos is never going to be a substitute for just like knowing how to do the math. You got to like make those decisions. Okay, so any questions at all about any of that?
Wait, I have a question. Is it okay if you could show the Desmos version one more time, please?
For this problem?
Yeah.
Yep.
So do you always have to add like x1 in order for it to work?
Yes. Yeah, so I honestly don't know a ton about like how Desmos came up with this, but this idea of regression, um,
Okay.
what it's doing is whatever values you assign for x1, it's plugging them into the equation.
Okay.
So it's like making x1 2, and then you're going to have an a and b that's unknown. And then it's making x1 3, and you're going to have an a and b that's unknown. And Desmos is just solving it immediately for us. So that's why you need the number of constants, which
Okay.
x1 is the variable. You need the number of constants to match the numbers here. Now, why we have to use x1 to signal that, I have no idea. It's just Desmos's syntax.
Okay. And one more question. For x1, you can put in any value, or does it have to be?
Yeah, good question. So here's the rules. You need to put as many values as there are constants. And then in problems like this, you just want to always stay away from dividing by 0. So if I accidentally put 1 and 2, it won't do anything because I'm dividing by 0 when I
Got it.
plug in 1.
That
But
makes
look,
sense.
yeah, I'll just do like, I don't know, I'll just do like, not that we would do these, 11, 12. And as long
Okay,
as I
yeah.
pick 2, it'll just work. Yeah. Because that's all it's
Okay.
doing. It's solving it so quickly. So, but if I only pick one value, it just makes up
And
a value that would work, but not necessarily the answer that we're looking for. But once you put a second value, which is anything I pick,
yeah.
and then if I
So
end up
it's
putting too
sorry.
many, go ahead.
So it's based on the number of constants there are, but like not the x1 constants, the other ones like a and b.
Yeah. So what's important is just in general in math, X is a variable, and then like
Yeah.
the A and B are considered constants, right? So the variable X we change to X1 just because that's Desmos' syntax. And
Mhm.
then that's our variable that we are assigning these specific values. And then, yes, we need it to match the number of constants. But if you're concerned, if you put in extra, it doesn't change the answer. So if I go back to something more realistic, if I just did 2, 3, 4, 5, whoops. If I put in too many values, it still gives me the right answer.
Okay.
So
All
just
right.
like start putting in a bunch of values until they
Okay.
snap, until they're the same values over and over again, and then you know you have the right answers.
Okay. Thank you.
Yep. But again, it's super important that we understand how it works. And then again, sometimes the tendency is to just think like, oh, I'm just going to use this every time I see a problem like this. But it's some
Yeah.
problems you're going to be probably wasting time by typing all
Yeah.
this.
Like this
And
one.
yeah,
Yeah.
possibly. Yeah, it's still not too bad. But then, like I said, you have to be prepared. The
Mhm.
trade-off is if you do a problem like this,
Yeah.
it gives you the wrong answer because there ends up being two answers, and there would have been no way to know that going in. So if you were to
Yeah.
try it for a problem like this, you get the wrong answer because they're not integers, and then you're back to doing it this way anyway.
All right.
So,
Okay. Thank you.
yep. Which is why you always need to know the math way to do it and then like the Desmos way when it applies. Okay, let's try number 7. This is one where I personally think that what we just learned would work, but like it's also simple enough to just square this out, hopefully, that I feel like doing it straight away would probably be faster. But again, it's like a personal thing. Yeah, so this one definitely would work using Desmos, but I am going to do it the other way because it also comes down to when we do it the straightforward way, if there's any like little shortcuts that we can take that can also help save time. So for instance, when we square something out, well, hopefully we know we can't just square each one of those individually. We got to imagine that we're foiling it. But if you know the kind of the shortcut for that, it's just this one squared, which is 9x squared, And then it's these two multiplied together and then doubled. So that's 12bx. And then this one squared is 4b squared. If you're able to do that, then doing it this way is just going to be quicker. It's going to be quicker than typing it all into Desmos. But if you're the type of person that really needs to write this out, which is, again, this is totally fine. If it's confusing to just go directly to this and you have to actually like do all this, then that you would probably be the type of person that would want to do this in Desmos. So there's definitely like knowing yourself and your strengths and weaknesses is a big part of this. But I'm just going to go over the like this way. So if you can get right to here, then it's pretty straightforward because then I see that A is 9 because the coefficient of x squared has to be 9. Now B, well, if A is 9, then this becomes 72. So then this has to be 72. And therefore B is 6 because 12 times 6 is 72. And then this is the constant at the end. They have to be the same. Well, C would have to be this 4b squared, but I now know B is 6. And 6 squared is 36 times 4 is 144. So C is 144. And then it just wants me to add those together. So that's 159. Right. And again, if any of that I did quickly seemed like too much, then definitely just throw this into Desmos with a bunch of x1s and a tilde, and you have 3 constants. So you just plug in. This one is not rational, so you can plug in any 3 values you want. Like, I probably would tend to stay away from 0, but I'll just do like 1, 2, 3, and you'd be good.
Yeah, that makes sense. I tried 0 first and it was like a weird number, so I do think 1, 2, 3 would work better. Sorry.
Yeah, it's a thing. Just like play around with it. It's not an exact. It's like the purpose of it is this regression, which has more to do with like statistics and fitting an equation to like a model. And we're almost like we're using it for like a purpose that it really wasn't intended for, but it's super useful. So that's why there's like these weird things that happen, which is why I usually only go over them when we're at like a more advanced level for the SAT. So it's like it's a good thing to add to what you know how to do with Desmos.
Got it. Thank you.
Mm-hmm.
Alright,
And if
got it.
anything, just keep playing around with it. If you're already committed to doing it and you see that a couple values you chose didn't lead to something, just change it to other values and then change it to, and then you'll eventually see the A, B, and C that is 9, 6, and 144. Once you see that over and over again, you know you've got the right answer. All right, let's just do a couple more. This is this. I don't think this would work with the regression in Desmos, but this is along the same lines of what we were talking about, but not exactly. So try that one. Okay. So first of all, the reason that the other regression wouldn't apply is because we don't just have like one equation equal to another equation. Like we have an equation that's given, and then they ask us like what this is equivalent to. So it just doesn't really fit the format of like just one, like 2 things that are just equal to each other. This one is pretty tricky. This is where it really comes down to understanding like forms of certain things. I did this in reverse earlier, so I guess it was just this one. When we squared this out, I talked about the format of squaring a binomial. This is kind of the opposite. We're going to like factor this. We're going to realize that 4x squared is really 2x quantity squared. And 9y squared is like if we take 3y and square it. And then I need the minus to match this. And where this comes from is, again, it's doing this times this and doubling it. So if we can recognize that this and this are equivalent just by understanding our like factoring and squaring patterns, then we realize that, all right, well, I need a 2x minus 3y. So I go over to here, whoops, and I'm just going to divide everything by 2. Because if I divide this equation by 2, I get 2x minus 3y equals 7t. And then I want to square it, so I get exactly what's over here. And I know when I square this, I get this. That's where all this came from. So the answer is just whatever 7t squared is, which is 49t squared. So we get that. Yeah, I think there would be a way possibly, like if you didn't recognize that, to like choose your own values, which is a strategy I like sometimes, but here it would be kind of difficult. Like you have to pick an x and y and get a t, and then plug that x and y in here, and then plug that t into each answer and see what was equal. But it is doable. Okay, so any questions on that or anything else that we did tonight?
Nope, that makes sense. And yeah, thank you for the progression. That'll definitely help.
Okay, cool.
Yeah, it was very helpful. Thank you.
Awesome. Okay, then I think we'll make that the last one. I'll post all this on YouTube and I'll email you the link and everything. So if you missed the beginning, you'll get to see those problems as well. So,
Alrighty then.
all right, have a good night and I'll hopefully see you same time next week.